So this is the farthest thing that humans have ever seen? The farthest galaxy, yes. The light from that galaxy traveled through the universe for nearly 13.5 billion years before it got to us. How do we know that? Because Z equals 14.3. What? Redshift, man. Z stands for redshift. You see, because the universe is expanding, light traveling through the universe over very long periods of time gets stretched out to longer and longer wavelengths, which consequently makes the light more red. That effect is known as cosmological redshift.
Okay.
And the longer that light's been traveling through the universe, the more it gets stretched. So if we could determine just how much the light from a given galaxy has been stretched from what it originally was, or in other words, measure its redshift, we could also determine how long that light's been traveling, when it was emitted, and how far away the galaxy that emitted it is. And we can do that. Indeed. Measuring the redshift of light is actually quite straightforward. The universe gave us a way to do it with atoms.
Atoms?
Yes. Here's how we typically do it. We collect the light from the object in question, like a galaxy, and break that light up into all of its constituent colors by passing it through a prism or something like a prism. We then look for colors in that light which are missing. These are called spectral lines, and they tell us which chemical elements are in that object. See, thanks to the way that electrons occupy different energy levels for the various elements on the periodic table, every element absorbs and emits its own unique set of wavelengths or colors of light. And that gives each of them their own light fingerprint that we can identify. That's how we can tell what an object in deep space is made out of, right here from Earth. Is that not amazing?
It is pretty awesome. And that's how we get the redshift too?
Yes, because here's the thing. We know precisely where each element's spectral lines should be from our measurements in the lab. But when those same lines are detected in the light of a distant galaxy, they are all shifted to the red end of the spectrum, indicating that the wavelength of the galaxy's light grew from its initially emitted size. And by calculating just how much it grew, we get our value for the redshift, Z.
And what do we do with Z?
Well, in general, we know that the greater that Z is, the longer that the light must have been traveling through space, and thus the farther away that the galaxy it came from must be. That's why when scientists talk about things at extragalactic distances, they often just refer to the object's redshift, because cosmologically speaking, distance is largely what redshift indicates.
Ugh, okay, this is a lot to keep up with.
Well, just remember this. Higher Z, farther galaxy. Repeat that.
I think I get it.
Repeat it.
Higher Z, farther galaxy.
Right. And the galaxy with the highest Z that has ever been measured is that one. Discovered by the James Webb Space Telescope. Its name is JADES GS Z140, and it has a redshift of 14.32. When we take that redshift, along with our best measurements for various cosmic parameters, such as the universe's rate of expansion, and apply it to the mathematics that describe the universe on the largest scales, Einstein's general relativity, we find that that galaxy's redshift corresponds to its distance being nearly 34 billion light years. Aside from the edge of the visible universe, that galaxy is the farthest thing that humanity has ever seen.